Okay, my name is Stephen Trotnic. I am with Blaine Allen and Alex, who I'm not sure his last name is because why? I don't know. Uh, I will be going through a tutorial on how to use Vivado HLS to generate HDL code from C++ programming. I'll be doing this through two example projects. Both of them will be different implementations of a calculator, of a simple 5-function calculator design, and we will get going, starting with how to actually create a project from Vivado at the very, very start screen. Vivado is pretty easy. As with most things, it has a nice intro screen. Let's see. We will create the project name, and we will store it, not there, in there, and continue on. This screen here is if you already have files that are that you're pulling in and importing, you can add them, or I guess you could create the files already. I haven't done it this way, so let's see what happens. New file. This screen is specifically to apply test benches to. You generally should only need one test bench for any project. I don't know why you need more, but there's that. This screen is set up to define solution names. You can have multiple solutions to any given project. You can set the clock frequency for whatever it is that you're working with, and uncertainty. That I'm not sure exactly what it does. Anyway.
What is a solution?
A solution is essentially the process of simulation, of C simulation, C and HDL co-simulation, and then the HDL that's generated from it. We are not working with any particular, we don't have any hardware to actually put this on today, so whatever board doesn't matter for the sake. But if you were to have hardware you're working with, this would be where you select it so that you, what your HDL works with the FPGA that you're working with. When you finish, you have a nice set of everything that you need. And since we're starting from scratch, we need to open them all. This is a simple panel. Once you have everything open and created, you don't really need any more. So for the sake of space, since I have a huge screen, I will close that. As I said, this is a simple calculator. It will perform the functions of addition, subtraction, multiplication, division, and modulus on two 12-bit operands. In order to accomplish that, we will utilize three different words. We will utilize a word or a variable called operation or operation type that defines which of those functions you're performing. We will generate an operand 1 and an operand 2, which are what the functions will occur on, and we will have an output. So for the header file, we'll need to do your basic header file stuff to create it and make it functional. I've already created all this stuff before, and to save time, I'm just copying and pasting it from an open text file so that everyone watching knows. For HLS projects, you need to include HLS stream.h. This is a library that allows you to easily create FIFOs that HLS knows what to do with. These FIFOs are used for, generally, though they can be used for other things, they're generally used for both input and output ports into the hardware design that you're creating. We also include APInt, which is a library for C++ that allows you to create fixed point values so that you don't have to use the typical integer, double, float, all that stuff. You can define how many bits your variables will use, which is very helpful when it comes to almost anything system-based in the hardware. And in order to actually utilize that, you can either use AP_int with brackets being what size when you define the variable name, or you can actually do a type define. This is a function of C++, and I probably don't need to explain it. where you give the type you're creating a variable name that you can easily reference later. Next, so one thing that I found while using HLS is the arguments to your top-level function will be any and all system inputs and system outputs. And if you have multiple functions, all of those inputs and outputs need to be moved throughout those functions. So it's actually easier to create a struct that has all of these values in them so that it becomes easier and you don't have to type out, like there's a project I'm working on that currently has 33 different values I have to move between all of my function calls. So a struct is a much easier way to do this. One thing that I found in my research is that the commonly accepted practice is to use what's referred to as an AXI word. And that references data types or axis, which is used in a lot of the pragma stuff that I don't know a lot about yet. So this word is going to represent, in this case, all of our inputs into the system. So we have the operation that's being conducted, whether it's addition, multiplication, subtraction, division, or modulus. And then we have the two operands that are being operated on. Oh, and I forgot, in this first function, I'm actually doing 17-bit variables, and then we will output to a 34-bit variable so that we can handle multiplication in case we need that many bit values. And then, since this is a typical C++ header file, we also need our function prototype for our actual main file. Inside of this, we will have, this is what I was talking about with the stream, the HLS stream in data. This will be all of our input ports. This stream here will account for all of our output ports, so all the data that we're outputting outside of the system. One thing to notice as you look over here in this panel here, this will start showing all of the different variable types and all the random data structures that you have throughout your project, or I should say within the file that you're working in, so you can keep track of things and find them a little bit easier if you're looking for stuff.
Quick question, Steve.
Yeah, go ahead.
So you have your scope resolution operator into HLS.
Mm-hmm.
Where is HLS defined specifically? Is that in the stream there?
Yes.
Okay.
And then, as with everything else, in the next example that I'm walking through, you can actually use the namespace, so you don't have to use the scope resolution and all that, just all the typical C++ stuff.
Can you open up that HLS stream.h?
I would have to find it.
Okay, no worries.
We'll go back through that after I've gone through everything and look through there. There's some interesting things that you can do with streams anyway, so it's not a bad idea. In terms of the header file itself, this is all that we need for this simple of a project. This is going to include other things, obviously, if you're doing a more complicated program, but this is all that we need for now. So we'll move on to the CPP. This is going to be your main function. And as such, obviously, we need to have our fun includes and our function definition. HLS is a full compiler, which is kind of nice because as you go through and you type stuff out, if you mistype something, you'll start getting it will actually identify misclicks and misspelled words and stuff. So if you mistype simple calculator when you're trying to do a function call, and it's easy to identify and a lot easier to find errors that way. It's actually kind of nice. Inside of this, what we need to do is to is this the best place? Yeah, we'll deal with this here. So inside of this simple calculator function, which this right here inside of our main function is what Vivado refers to as a top-level function. This is what is going to be converted into HDL and put onto the FPGA fabric. So anything that you actually need within your hardware system needs to be either in here or in function calls from this function, this top-level function here. You can do function calls to other functions, and it will still be created, so that's not a big deal. Actually, I need to, real quickly, one thing you need to do for every project and I forgot about this, is go into project settings under synthesis, and you need to select which function you've created serves as your top level function and is the one that will actually be generated into HDL. And of course it's, here we go. Oh, okay. I haven't actually tried to generate this yet.
Save your files first.
Oh, you want to know? You're right, it hasn't actually. Maybe that's why. Usually I don't actually try to build it until later, and so there we go. Good call, Alex. Okay, so we've set it up, and now it'll recognize that as your top level function. So inside of this stream, essentially when you create the test bench, you're going to feed all of the test data that you need to test all the functions of your program into this stream FIFO. So what we need to do is we need to start reading in information from that FIFO to be able to utilize it to be able to read it into our hardware system and be able to do things with it. That is actually what this statement here does. So we have our variable type, and .read is the function call for popping information off of the FIFO. .write, as we'll see here soon, is the function for pushing stuff into the FIFO. We are going to, because it's a FIFO, you can only read the data one time before that data is erased from the FIFO and it needs to be stored someplace. So what we're going to do, and this is the case with all of your reads, you pretty much need to store them into some sort of a temporary holder that you can do stuff to the information after, unless there are some really, really weird situations where all you need to do is just read the information out one time. You don't actually need to do any processing with it. Next thing we're going to do, since this is a simple calculator and we have 5 different functions, we're going to do a very, very simple switch case to determine, we're going to try to do a simple switch case to determine which function of the calculator we're implementing. So here we have our switch, which is going to be the operation member of the word holder struct. For 0, we will do addition. And this is what I was referring to as the write function. That actually, what this is going to do is this is going to take this function call here, the addition function, which will return the addition of the two variables, and it will write it to our output stream so that later on in the test bench we can output all the data that we have generated and see if it matches with what our expectations are. This is just a simple case, so 0 is addition, 1 is subtraction, 2 is multiplication, 3 is division, 4 is modulus. And that is, for this program, all that we need for the calculator. Once I actually try and simulate this, these will fix themselves and they won't be unknowns. Right now they're unknowns because I haven't compiled and it doesn't recognize any of this stuff yet. So let's actually go over and generate these functions real quickly. And here we just have our function prototypes, nothing special, and all of the functions themselves are ridiculously simple, which is why I use this as a program. So as I mentioned, whenever we're doing stuff, we pretty much need to send all of the input variables through all of our functions, which is why having a struct that contains all of those is really convenient. So for our addition function, we're going to return a fixed point of 34. And we're going to return the addition of the 2 operands that we fed into the system from our test bench, which we will do here in a couple seconds. And the same thing with the subtraction, multiplication, division, and modulus. That is very easy and very simple. So now we'll move on to the test bench. So the test bench, in case you don't know, or as with the test bench here, even though it's written in C++, still functions as all the other test benches for every FPGA. The purpose is to create your inputs and outputs in the test bench, feed the inputs the data you need to check that your outputs generate what you need for the system to be working. So we will get our includes because those are important, and here's where your int main is going to reside because this is actually your the first function in the system, even though it's not the main one that we actually need for our hardware. Here we're going to create at the very top. This is going to, as with everything else, this is going to create all of our input, output, and temporary variables that we need to check the hardware system. We're going to create our FIFO. We're going to create our output data, and we're going to create the actual end data itself that we'll use later on in the system. And as with other structs, since this is a struct, we're just assigning zeros to each of the member variables. The next thing for this for a simple test bench like this is to generate the information that we want to feed into the FIFO. So we have 5 functions of the calculator, and we need to test all 5 of those. We need to test all the addition, the subtraction, multiplication, etc. So to do that, we are going to assign each member of the struct the data that we need to get an output that we desire. So if we're going to check addition, we'll assign 0 to the operation value, and random, easy to generate and easy to assess values for the sake of the actual addition. Once all of these values are stored into the struct, we then feed that struct into the FIFO that will be used inside of our simple calculator hardware to process the data. And it's this simple, that's all it is. Then we'll go through subtraction, multiplication, division, and modulus. By technicality, since all of these values are the same, this struct exists like any other variable. Once you assign values, those values will stay until you've reassigned the values. So since all of these operand 1 and 2s are the same, I could just assign these one time. But for the sake of the calculator, these won't necessarily be the same all the time, so I'd just reassign them every time. I could comment these out, and it wouldn't change the function of the system. However, with the FIFO, as soon as you read information that is on the top, that information leaves and it isn't there anymore. So you need to make sure you save it to a variable that you can do stuff with later. Now that in theory, once this is run, this will feed all 5 of these sets of input data into the system to be processed. Assuming that's happened, now we have to do something actually with that data, because we haven't actually called the hardware yet. In order to do that, HLS has a very convenient function call for its streams called empty, which is just a simple Boolean check to see if there is information in the FIFO or not. In order to do this, in order to run this as many times as we need to, based off of however many input values we have on the stream, we do a simple while loop. So while the FIFO is not empty, we're going to call simple calculator, which is our hardware. And we're going to send it the FIFO and the output data streams. This will in the hardware, this will actually initiate all of the stuff that we've written out here and generate everything, and it'll start the process. By the end of this, because of how we have it set up, we will have a stream of our output data, but we haven't actually done anything with it yet. So whereas this one initiates based off of the inputs, we're going to do another while statement that initiates off of the outputs, and it's the same thing. While the output stream is not empty, we are going to assign a temporary variable the value from that output. One weird thing that I haven't been able to figure out how to do yet with streams is to cascade commands off of them, off of the read function, the read or the write function itself. So I haven't been able to figure out how to do outdata.read and then shift this a certain number of bits or whatever. This is kind of an isolated function that does one thing, and it's difficult to combine it with other things in one call. And these reads, these fixed integers or unsigned integers cannot be output through the printf function. If you include standard I/O, you should be able to use cout, I believe, but I haven't done it, so I don't know everything that's involved with making it work, and I'm not even positive that it does work. So we're not going to do it. We're going to use printfs because that's what I've been using.
So, quick question.
Yes, go ahead.
So these are data streams, I'm assuming they're data streams in the traditional C++ sense. Does that mean that the Vivado libraries that we've included, do they overload the, I guess, the stream operators, the double carets?
No, because actually, to be honest, I don't know. HLS restricts your ability to do system calls and dynamic memory and a few other things that you can't do. For the sake of the seed, we don't need those, which is really convenient. For the sake of a lot of sequential hardware things like what I'm doing at Sandia, it's actually still very convenient. I'm not certain if it overloads those functions or if it just creates new functions for stream. I haven't used the two of them together, so I don't know how that interaction plays out. It'd be worth playing with. I'm not certain. Sorry.
Not a problem.
Plus, these streams are actually FIFOs. I guess Cout and all the other streams are a form of a FIFO as well, so it might override it. Anyway, theoretical conjecture aside, if we were to and we also need our return 0. I did not include any error checking. I did not include any of the more advanced things that you can and should do with C++ programs to make sure that inputs are valid and all that, just because it's a simple program and it's not really necessary. HLS doesn't change how you do all those. They're all just logic comparisons and calls anyway, so I didn't do any of that here. So we're just simply going to return 0 at the end of the project. This is all that we need. As I've mentioned here, this is this printf here, where you just simply try to print out the fixed point integer, is not the correct way to do so in Vivado, and will pull an error. So I'm going to save it and run it just to show you what that error is, so that in case you run across it, you can remember. It might be a little easier to remember. This is one of my more common errors that I came up with initially. This is the entire system. You don't need anything else, assuming, of course, that I'm not completely unlucky and Murphy's Law isn't working against me for the moment. This should compile with this one error that I have in here. So now that you have the test bench created, there are 3 more steps to getting this on the board. The first step is to come up here into Run C Simulation. This will run through, compile, and output into this console anything that you have in the printf. So this is how you check to make sure that your code is doing what you think it should do. The next step, once you have a successful C simulation, is to come over and run synthesis. This synthesis process will take the C++ code, generate HDL from it in either Verilog or VHDL, depending on what you choose. And the final step, well, actually, I guess there are 4 steps. The third step is to run the C++ and RTL simulation together. So what this essentially does is it runs through the C simulation one more time, records what all the outputs are, then it runs through the HDL code. Excuse me for a second. Runs through the HDL code, records its outputs, and compares them to make sure that they're the same. If they are the same, it will report a pass that the RTL is working and that you should be good for exporting onto the FPGA, which is the final step. So we will run this real quick. Vivado has an annoying pop-up that I don't like, so I choose not to ever show it again. And since you made me make my screen really big, I can't get to the OK button. And then we just work through this compile. Here's another message dialog. This will tell you if the simulation is run without errors, this dialog should not pop up. If there are errors, it will let you know. And we have our one error that it cannot pass non-trivially copyable types of fixed points. So in order to get around that, the fixed point library has a convenient function which allows you to typecast the fixed point into a standard C++ variable. In this case, an unsigned double, essentially. This allows you to print out and makes life easy, and we should get appropriate outputs. Unless Murphy doesn't like me, which he usually doesn't. You would think with just copy and pasting you wouldn't be able to mess things up and you'd get stuff right. So once you do the simulation, Vivado generates a csim log, which will show you all of the outputs that you generated with your printf statements. It will also, in the console, generate the exact same information. It's duplicate. It's the same information. There's no, you can look at one or the other. I have checked these before now, and these are the correct values. We do have a functioning calculator. We could feed it whatever values you want with whatever the 5 operations we want and get valid output from it. One thing to note is that in the test bench, these printfs are not limited to the test bench. So if I had, and I did this quite a bit trying to get these codes to work, if I had something go wrong inside of my CPP or one of my function files, I could printf hi, and it should throw that. If we get in here, it should throw that into the output. This is the like with all C++ code. This is the common way of doing checks on your data, make sure to figure out where problems are.
So how do the printf statements translate into the HDL?
The printfs, I don't believe do. They are system calls within HDL. I don't believe that they actually follow through into the code, because I mean the hardware has no way, unless you design it as such and tie the printf to like an LCD screen or something. It shouldn't have any way to actually print out a printf.
That's kind of what I thought.
Yeah.
So that makes sense. All right, cool.
Do you guys have any other questions about this project? That's all it is. It's a very simple project. I just wanted to keep it basic and show you what HLS is capable of and some of the tools that are useful for generating systems.
Awesome.
You good, Blaine?
Yeah, I think he's good. He coming back.
Blaine abandoning me in the middle of my presentation. Well, I should have expected nothing less.
He's back already. It's momentary abandonment.
Oh, okay. Well, then I don't feel quite as bad. Okay, now that, do you have any questions about what I went through in here, Blaine?
Very clear.
Okay.
Very clear so far.
Good, good. The way I haven't used this particular style where we define a struct and use that struct in the stream. In my mind, this would be useful if you had, say, a system that has either a bunch of serialized inputs that you have to meld all of them together into a coherent word, or if you are, say, using parallelization to transmit data and you have to combine all the individual ports into one word to be able to utilize the data. That would seem to make sense to me. So because of that, the next way that I'm going to implement the same function is using a single bit stream to pull all of the information in. So essentially this system assumes that you're just getting information and you kind of generate the words within the hardware itself. The next way I'm going to do is kind of assumes that some exterior source generates the words and streams them in serially. In my mind, all of these are probably going to, even though this is kind of a parallel operation, in air quotes, all of these are going to have to be streamed bit by bit to get into the system anyway, just based off of how hardware works. So while the next example of the same thing is going to put all of this information into one stream, it is conceivable that each of these could be their own port that is each streamed serially, and then you would use what I'm about to show you on each of these individual parallel streams and then combine them later, if that kind of makes sense.
Yes.
So we're going to create, actually for this one we're just going to open the project since I've already shown you how to create a new one. You can only have one project open at a time, so yay. Crap, which one did I do? Simulated? Yeah, this one. As I said, this is the exact same thing. Oh, there we go. This is the same thing as the last one we did, just implemented in a different way. Okay. For this one, we're actually going to start with the test bench because you already know how the function operates. So we're going to scroll through here and show you, kind of try and show you how to generate a sequential an input stream, a 1-bit input stream. This could be the same thing if for some reason you actually could manage to stream 4 or 8 bits at a time, but that doesn't seem practical to me given what I know of hardware, so we're just going to do it this way. Typical function protocols. For this one, instead of using the AXI word as the struct, what I decided to do was to define my own struct. The AXI word is just an arbitrary word that people use. It doesn't really matter what it is. And this will have the input stream. This will have the output result. It will also have a temporary value that we pull the data from the stream in and create a word out of. And then it has the stuff that we need actually to pass to make the whole system work. So we create it. Here we are going to actually send in these words as the words that we stream into the input FIFO. These are the exact same values that I used in the previous one, so addition, subtraction, multiplication, division, and modulus with the same 12-bit values, AA555. Where'd it go? So for the write stream, we are essentially going to take the word that we created. In this case, we'll use the first one, which is the addition of 2 values. And we're going to use a for loop to rotate, since we're taking a 28-bit word, and we are forcing it into a 1-bit stream, however far you rotate it over, it's still going to truncate everything past it. So we're just going to do a very simple for loop that walks all the way through the word and sends it into the stream with the write command. Not very difficult, kind of annoying to work through and get the logic right, but be careful with how you do this. I think this is, we talked briefly in one of our previous conversations about the concept of either big or little endian data transmission based off of backwards or forwards and how it works. I think this is somewhat the reason for why those two exists, is how it decides to translate data, whether it's frontwards or backwards, relative to how the information is coming into the system. I don't know which one I'm doing. I'm doing the one that makes sense, where I start with the most significant bit and stream it in that way. So this process here will... Oh, sorry. Go ahead.
Oh. We were just snickering at your comment of...
My way's the right way.
Yeah.
What this will essentially do is create a 140... A FIFO of a depth of 140 single bits, which is 5 28-bit values. So as before, we have to do something with that. So we are going to, while there's information in this FIFO, we're going to call the streaming calculator, and then inside of this, if we have a valid word, because remember, we only need 5 outputs, not 140. So within this, we have our valid word flag, so that if once we have pulled in 28 bits from the stream, we will flag that as a valid word, we will process it, and then we will output the result. The advantage to doing it this way is if we have another system after this one, this generates an output, and we can functionally use the output without having to shove it into a stream FIFO at the end of it, and it saves some of the fabric. So if this were to link to another system, it would send one value in, the other system could immediately use it, and we don't have to actually set up a FIFO at the end, which I find to be very convenient and useful for a lot of different things. Beyond that, our actual print statement in this case is simply the switch case so that I could check. I was having issues with it working properly and getting all the information, so I actually isolated exactly which function I was using, and this is just a simple print. There's nothing difficult with it. Inside of the header, I mentioned, actually we've already been over this, I mentioned what we're sending and why, and then so we're going to the CPP. So in here, we are going to have to reset the valid word flag every time it comes into here. It's easiest to do this here rather than anywhere else, so this is where it's been done. Here we have our word generator. This is going to take our input stream, read in 28 values, shove it into this value here of the input word, which will be our temporarily held word that we actually process information on. And then we will continue on. If we have a valid word, then we will actually do the calculations from that word. So inside the word generator, I had to do some trickery here. With the project that I'm doing with Sandia, I can't remember how he did it, but Willie actually typecast one of these. This right here is a single bit word, and this is a stream of a single bit word. I can't remember how he typecasted it, but he essentially allowed skipping this process of taking the single bit word and throwing it into a 28-bit word. I don't remember how he did it. I'll look it up and update this later, but I had to do this a long way here. This is going to take the value. This input offset is simply showing which location inside the word you're getting. You're going to move it over and create the overall word with this. Are there any questions? Hopefully, I'm probably going way too deep because you guys have some programming background, so you should understand what's going on. Hopefully, maybe. Yes? You guys good?
Yeah.
Okay.
Yeah, good.
And then because we have different flags and stuff, we need logic to reset those flags. So once we get to 0, we've gone through an entire 28-bit word. So we need to take the word that we've slowly been generating off of each input bit and then assign it into our temporarily stored variable. We need to set the valid word and then reset our counters. If this is not a full word, we decrease the offset and we set the valid word to false. Simple, simple. Next we will go, back here into the CPP. So if we have a valid word, we're actually going to take the information in it and we are going to do functions on it. Now here we have a 28-bit word where the first 4 bits are the operation type. The next 12 bits are the first operand, and then the final 12 bits is the second operand. So we're going to have to find a way to extract that information and do things with it. The nice thing is the uints inside of C++ have this really great function called range, where you can explicitly pull out the exact bit values that you need, which is amazing and makes life a lot easier than trying to do this manually.
This is essentially doing Verilog in C++.
Yeah, pretty much.
That's exactly what this is.
Without having to do the Verilog syntax, which is the most important part.
Verilog syntax isn't that bad.
It's not, but
yeah, this is a really, really good kind of in between them.
And this, like I said, a lot of this is very contrived because it's a very simple project that I'm trying to show what it's capable of. Some of the stuff isn't necessarily as explicit. If you're doing a more complicated project, it's not quite as clear.
Yeah.
But it's easier to see, at least for me, because I'm used to C++. So,
quick question.
Yeah.
So everything when we set up operation type, and I get the feeling you're going to be getting this, but I want to make sure I understand it.
That's fine.
We're setting, say, pins in hardware range 28 or 24 to 28 in C++. That's ported over to Verilog. We can then access those pins how we want on the non-C++ side.
Essentially what this will do is this will create this will use a series, in this case, of 4 flip-flops to create a new variable in the hardware on the FPGA. And these flip-flops, we would, like you said, have the ability, these will all be tied together, they will be tied in order, and we will be able to do stuff with them as they are created as a 4-bit word.
I guess the question is, how flexible is the modularity post-synthesis?
In terms of what can we go into the code and actually do isolated things with them?
Correct. Will we have to go back into the C++ and re-render, or resynthesize, or
if there's an issue with how we implemented it, we could go back in and resynthesize. We could, if we wanted to, go back and actually sort through the Verilog and try to find it and fix it, but it would probably be easier to do it through C++ because, as I mentioned before, unfortunately, the code that is generated from HLS, at least Vivado's version, is not very clean. And even from people who work with, whose job it is, and who have like master's degrees and working with FPGAs and working with Verilog, they have identified that this process creates code that is generally pretty much unusable when it comes to sorting through it on a human level and doing stuff with it. You can, but it's a lot harder. It would most likely be easier just to do it through C++.
To clarify semantics, not clean, but very efficient and compact, right?
It is a very efficient implementation of the FPGA fabric, correct. As I've talked to you about, but Alex probably doesn't know,
Yeah.
essentially the project that I'm doing at Sandia is to take an entire system that has been generated on one FPGA that is not radiation hardened for a satellite, and then create a truncated version so that when that system fails, because we're pretty sure it will, we have a backup on a radiation hardened FPGA that we can still use to get usable data. The problem is we didn't use that FPGA in the first place because the overall size of the fabric created from Simulink to create this system was too large for the radiation hardened FPGA. Having done this and having probably 90% of the functionality created in HLS of the overall system, I'm using about 3.5% of the smaller radiation hardened FPGA versus a system from Simulink that you couldn't even fit on the FPGA in the first place.
Okay.
So this is significantly more efficient than Simulink's version. With that being said, that doesn't necessarily mean optimized. What the seed is going to be a much more optimized version, so we might not be able to use it as cleanly because there's a lot of stuff where we really need to control the nitty-gritty of how the bits are being used. With that being said, though, that much of an improvement has got to be more efficient, at least to some degree. If nothing else, you're not going through as many gates. So we'll see what happens when we start using this, if we start using this, and see where it goes. But does that answer the questions that you guys had for the moment?
There are a lot more like gate count kind of questions, but as far as not interrupting the flow of your presentation, no questions so far.
Sounds good. Okay. So just a quick recap, we've isolated the components of the word that we need to function for this program. So we essentially I could have done another switch case here. You could do if statements. It doesn't really matter. This accomplishes the same task. In this case, I actually stored the result within this struct, unlike the last example, so I don't need a separate output variable. It's just another variable within the struct, which is another way that is very common. A lot of the AXI words include all input and output variables. And this just does our math operations, and that's the entire system. I believe we've been through each of these and have explained the whole system now. So when we run this, we should...
Which button should you click?
Oh, dang it. It is the run C simulation.
Okay.
And apparently this dialog doesn't remember different things between different projects, which is annoying, but just remember that dialog box pops up. And here again we have the exact same values that we had before, except this time we have identified what the operation is that's being performed. But it still works just as well. So if we do the run C synthesis, which would be the next step in theory, I never identified a top function. I thought I did that.
You did that on the last project.
Well, yeah, but I imported this, and I thought I had done this before when I tested it all out, but apparently not. So, hey, look, now you get to see how to do the setting top function again. Yay! And I thought you needed the top function for simulation, but apparently you only need it for synthesis, which kind of makes sense. Here, this is not doing any simulation. This is just generating the HDL code based off of the C code that we have up here. And this should result in a report that identifies, I think this report is what identifies how much of the various FPGA fabric is being used. So we look at this, we have timings in terms of how long it takes to generate. We also have latencies, a bunch of other fun stuff. And down here, which is kind of the more, well, one of the more useful things, is a summary of each of the components, the flip-flops, the lookup tables, the RAM, and the DSPs that are being used to actually accomplish this. And as you can see, we're using very, very little, which makes sense because it's a very, very simple project. Next step would be our co-simulation. So this is the C and RTL co-simulation. This, again, apparently Vivado really likes their stupid little pop-ups, which I can't get rid of. So in here, this is where you would select whether you were using Verilog or VHDL. And you can set up different other types of things, reduce disk space, optimization, locations, all the fun, stupid things that we don't care about. We'll do Verilog this time just to see it. And then we will generate and see what we get. Here, this is going through the simulation to record what the results are, and then once this goes through, if I remember correctly, as with, like, even with Simulink, the first simulation takes the longest, and I think it kind of caches things, and any future simulations, I think, go faster, if I remember correctly. So
Yes.
it is fairly convenient. It's just that first one that's really annoying.
And this tool is 50% faster than Quartus 2.
Awesome. Wonderful.
And this is a pretty simple project, too. This is kind of sad. I will take it, though, especially if we can get this to work with the seed. That would be awesome.
Oh, yeah. So it does specify C, but this is Vivado HLS ports over C and C++.
Yes, that is correct.
And unless I'm crazy, you're actually creating a C++ file, but it doesn't make any distinction in HLS of whether or not you're using C or C++, or does it recognize based on?
It doesn't recognize it. It just generates.
Okay, cool.
So way up here, where is it? Somewhere up here, you actually saw the C outputs. I saw it flash by briefly, and then I lost it. So it did do the C simulation. Down here, it produces the results from the Verilog simulation, and it results with a pass because the two match up and are the same. So once we have that and we're satisfied with it, the next step would be to come up here and export the RTL onto the board itself, and then we would, in theory, have a functioning board if we had a functioning board we could work with. And then that's the project. As I said, I think this example here, the streamed example, is going to be necessary every time, even if you have parallel ports, just because you have to be able to stream the information from the port and then construct the word anyway. So I think a combination of this in addition to the other project where you have multiple ports for the word and the two operands would be a pretty good realistic expectation for what a real system would most likely look like. And as I said before, these are really, really simple. The only thing that I haven't covered in here is a concept called pragmas. And Blaine and I were talking about this a little bit before you walked in, Alex. Pragmas are an HLS construct that allows very fine control over the actual generation of the FPGA fabric. So you can do things like you can kind of lockstep different functions so that they occur at the same time. You can control how long it takes to send information from the stream to the system. So you can make it sure it's always one clock cycle instead of, say, sending a value all the way through the system, waiting for an output, and then sending the next value. These input FIFOs that I was telling you about, that I was talking about, these streams, if you don't use pragmas, these are essentially unlimited FIFOs. Like for here, we have 140 bits. I've used 4,000 bits going in, 4,000 entries into a FIFO. You can use the pragmas to restrict the depth of these FIFOs down to a particular amount, so you can't overrun it, and then it'll start and then you would have to start adding error correction, not error correction, but handling, where if it overloads, you need to be able to do something with the information, and that's going to be more of what we have to deal with our with the FIFOs and the storage from each of our individual little processors and all of that. So there's a lot of stuff you can do. I haven't had to use pragmas yet in my my Sandia project, so I'm not exactly sure how they implement or the actual practical aspects of them. I only know of them in theory, so I can't speak on them too much, but that's the only other real aspect of HLS that I haven't discussed, so that I haven't gone over in these examples.
So there are a bunch of more examples on pragmas on a certain document. Where's that located?
There are four files that I uploaded to the up to the server, up to our Google Drive. One of them is an HLS tutorial that is very basic, has some stuff about pragmas, has some stuff about the top level function, a lot of the stuff that I covered in here. Very good thing to read through and get a handle on. Very good basic information.
Which one is that one titled?
That one is Vivado HLS tutorial.
Okay.
The second one is a system design PDF put out by Xilinx, which essentially goes through and gives a bunch of examples for different types of systems you can create. It includes state machines in C. It includes various data parsing type of projects. And it includes a fairly intricate, complicated project of some sort of like an IP routing system that you can download all the files from the website. I already downloaded those and stored those as a zip file inside of the Vivado HLS folder. And then the fourth document, that was the third document, the third file. The fourth file is a zip of these two projects that I created here today that you can download and play with and do stuff with if you want, that you can load into Vivado and get working.
Cool.
So.
Awesome.
Do you guys have any particular questions? And if not, I will probably end the recording here, and then we can talk a little more if you have more complicated, in-depth stuff that we just need to talk about for the project.
One added comment. I was looking in Vivado HLS, and under Vivado, under help tutorials, there is a very large document on extra material on how to do a lot of stuff like what you did today. It's 272 pages worth of tutorials, synthesis introductions, and how to do it seems like almost everything with HLS. So it seems like a really good documentation for just using HLS.
Cool. Yeah, I think I found this in my research before I started playing with it at work, and I run through, and this is where I got a lot of my initial information from.
Yep, that's it.
So yeah, this is also another good document.
Do you have, could you put that one up on the drive, same folder?
Yeah, I'll do that. Eventually. I will not do it quite yet, but I will do that once I'm done here. Anything else that you guys have questions on for the sake of this walkthrough?
Yes, I think I have a question.
Okay.
So I saw the checkbox for doing optimizing compilation when generating or when synthesizing the HDL. I also saw when importing all of the C files, there were C flags that you could set for each file. I guess what standard C and C++ compiler flags are generally supported by this? For example, can you do linking time optimization or different compiler optimization levels, and or is that part of the optimization process that it does?
That's a very good question that I don't have the answers for because I haven't had it to go through and use that so far in anything that I've done with it. I believe the compiler that this uses is GCC, so I would imagine that any of the typical flags and stuff that you are used to using, any of those projects and tools are available. As with most compilers, you still have the ability to debug and set flags and stop points, which I didn't go through and probably should have mentioned before. But this is essentially a full compiler and C++ IDE. You can do pretty much anything you want in here. And as I said, it's really fairly convenient if you were to change this to say you mistype into a uint26. Since you don't have this defined anywhere, it's going to show you that, hey, look, we have an error. We don't like this. You need to fix it. So, I mean, it's actually, even just programming in this is actually not bad. And I've actually fairly enjoyed it. It's pretty useful and a good tool to use.
I have a question.
The answer is I didn't do it.
Did you plead the fifth this time?
No, I just didn't do it. I'm just straight out telling you I didn't do it.
Are there any bugs that you've noticed so far that would be good for us to know about, or any hurdles that you've overcome with Vivado?
Very good question. I haven't run across any bugs that have prevented me from doing anything that I've done. Granted, everything that I've done so far has been pretty basic and minimal, and like I said, I have not yet been able to figure out how to take alternate CPPs. So, like for instance, if you were to create a class, the general CPP, C++ good programming practice is to create a separate CPP for the class, and then header files for all the various things that the class can do. I haven't been able to figure out how to add multiple CPPs to this, like secondary CPPs. And as I said, I'm pretty sure that's just an issue with how I have my include set up, and I just need to work through it. But other than that, I haven't really noticed any particular bugs, anything that breaks the system. And the biggest thing is just, there are sometimes, and I'm not sure what causes this, if I'm working in the test bench and I have a whole bunch of prints here, print statements here, like all these, and then I decide to, for whatever reason, come into here and check, say, the validity of this if statement, and I do a printf here, this will occasionally, and I'm not sure why, override print statements from other files, where it will only show this one and it won't show others. It doesn't happen all the time, and I'm not sure how I end up resetting it so I can see other things, but that does happen occasionally. I've tried things like going in and just retyping a new print statement inside the file that I'm looking to actually get information from, to kind of update that as the most current one to see if that fixes it, and sometimes it does, sometimes it doesn't. That's just something that you might have to play with and kind of run it enough times that it finally catches and sees all the other print statements, if that makes sense.
It seems like it would be a compiler caching error that you would have to just do a fresh compile.
It is possible. As I said, eventually it just sort of works itself out, so it's probably just simply that, where you run enough simulations where it flushes the cache and gives you the outputs that you need. I think that's all. Like I said, it's actually been a decent joy to work with, considering how much time I've spent inside of this program for the past 6 weeks. So with that, I think I will at least end the recording here, and then we can stick around and talk and see if there's anything else we need to discuss. So thank you for your time, and I will see you guys.